Take our time. Let's begin by reading this and let's see what we have here. So we have that a scientist is studying the relationship of two quantities S and T in an experiment. The scientist finds that under certain conditions, as the quantity S increases, the quantity T decreases. After taking measurements, the scientist determines that the rate of change of the quantity X with respect to the quantity of T present is inversely proportional to the natural logarithm of the quantity of T. Which of the following is a differential equation that could represent this relationship? Okay, this means, right, that, okay, what do we have here? So first thing, okay, the rate of change of the quantity of S. The rate of change of the quantity of S, that is ds dt, right? We need to know that the rate of change is your derivative equals. That eliminates this first choice here, okay? That gets rid of that, okay? Now the rest are ds dt. Okay, the rate of change of the quantity of S with respect to the quantity of T is inversely proportional. Now let's remember what we have for inversely proportional. Y is inversely proportional with X, or X is inversely proportional to Y. This is inversely proportional, this relationship right here. That's what this means. Inversely proportional. Okay, now, since it's the case, now what are the quantities involved here? So in this case, what's taking the role of y is this ds dt. Now what's taking the role of x? The response with respect to the quantity of t present is inversely proportional. So it's k over 2 the natural logarithm of the quantity of t. The natural logarithm of the quantity t, know that that's ln of t. Natural logarithm of the quantity of t, that's ln of t. And now you have your answer. Whichever one says this, what is it? C. C is the correct choice. All the other ones are incorrect. C is the correct choice. And you guys should see how it is that I went about doing this. Every single piece in this sentence, right? I mean, this sentence was it was an irrelevant sentence. Okay, I mean, like, we could use it for more information, just illustrating that it's not a proportional relationship. It's an inversely proportional relationship, right? Because in a proportional relationship, it means that as one quantity increases, the other one will increase as well. So this sentence that I'm crossing out here, it deliberately says that as S increases, the other quantity decreases. So you know that using that sentence that it's not a proportional relationship. Then it deliberately tells you that it's inversely proportional to the natural logarithm of the quantity t. And then you just write this here. You use this. This is sort of the heart of it, right? The heart of it, where you get your equation from, is right here in this sentence. After taking measurements, the scientist determines that the rate of change we need to know. What do we need to know about that? The rate of change of the quantity S. That we need to know is ds dt. With respect to the quantity t is inversely proportional. We need to know inversely proportional means this. We need to know what they mean when they say the natural logarithm of the quantity t is ln of t. Okay, and then we fill in everything that we know to get this equation as a whole. Okay, now let's look at this next one. Okay, a jogger runs along a straight track. The jogger's position is given by the function p of t. So the position of the jogger is p of t, where t is measured in minutes since the start of the run. During the first minute of the run, the jogger's acceleration is proportional. So the jogger's acceleration, right? Okay, so let's say this is the position. The derivative of position with respect to time is velocity. And then the derivative of velocity, or the second derivative of position, d squared dp dt squared, right? That's how you write the second derivative, right, of dp dt. You put the 2 on the d on the top, and then you put the 2 on the bottom by the t. This is just saying the second derivative of the position function, right, is acceleration. So we need to know this like chain, right? We need to know that if this is position, the derivative of position is velocity, and then the derivative of velocity is acceleration. Okay, so I just wrote this because I know I'm going to have to use it, because it's talking about the jogger's acceleration is proportional, k, times, and it's proportional to the square root of the time since the start of the run. K times the square root of the time. Which of the following is differential but best describes this relationship? It's whichever one says this here, which is C. Okay, practice, go through these ones, okay? The square root of the time, we need to know time is t in this case. Okay, we have something like that. So then therefore it's just k times the square root proportional to the square root of t. The square root of t, k times t. And we needed to know that the second derivative of position is acceleration, the first derivative is velocity, and the derivative of velocity is acceleration. And you write the second derivative like so. Just notation then, okay?